So the next thing we're going to consider in the context of actually applying activity to situations where we're having chemical behavior of ions affect the chemical system. The next thing we're going to talk about strong acids. The thing about activity, especially when we're dealing with ions, is you kind of have to think about what the chemical reaction you're looking at is doing. So the reason I'm going to talk about strong acids here is we just got done talking about water and how salts, even if they don't have acidic and basic properties themselves, can affect the pH of water. And it was all about making arguments of sort of ions finding each other and going back towards the reactant side. For something like a strong acid, the pH of HCl is going to be definitely affected by the activity of H+, especially at high concentrations. But the difference in the arguments that we'll be making now is that there's no path back to the reactant side. When we think about HCl and we write the reaction for HCl, right, and how it acts when it goes in water, we treat it like a full dissociation. It makes fully H+ and Cl-, just completely. What the activity measures, right, is going to be the free H+ that there is, okay? But we're going to change up our arguments, and that's what's sort of hard about activity. You have to think about the chemistry and what arguments you're actually making. We're going to change up our arguments. If we have a non-dilute solution and there's a bunch of H's and Cl's, it's not about these guys finding each other and there being an equilibrium constant and they can go back towards that side of the reaction, right? When we deal with activity, it's again kind of, well, how often do you expect to see just a free floating H+? Just an H+ where its ionic atmosphere is not being affected by a Cl-. Because that's what we're going to be measuring with this activity of H+. So what happens is this idea that you could get some ion pairing, where remember, if we're dealing with an ideal solution and we're looking just for the concentration of this guy, because we're assuming that all of them are just free floating by themselves, if you have a really like non-dilute solution, a really concentrated solution of an acid, a strong acid, right? The likelihood of an H+ and a Cl- finding each other is high. So if the activity is describing how much free floating H+ you have, okay, and there's no pathway back to the other side, right? These interacting strongly and pairing up, right? That's going to affect what you see in terms of this chemical behavior. So if I put a pH probe down into a solution and it's trying to find free-floating H+, you'll actually find less free-floating H+ by itself because these Cl- are going to be affecting how often it gets to that probe. The activity of H+ changes based off of the ions that are in solution. So the arguments sound the same, but we have to keep this in mind. What do we expect to happen with the pH? For water, our pH actually decreased when we put some salt in there and when we considered the activity of those ions. For this strong reaction, our pH is actually going to be a little bit higher in actuality. Because it's not about H+ escaping to the other side. It's all about how many free-floating H+ do you have. Okay? So the easiest thing to kind of do is, again, apply a numerical example to the situation. Right? So let's answer this question in two different ways. What's the pH of a 0.0010 molar HCl solution? That's not even super concentrated. That's not like 12 molar HCl that you get out of the bottle or anything like that. But it's in that range where, all right, we're not super dilute. And we're in that range where, all right, we might actually get these ions interacting with each other and changing their chemical behavior. Especially for a strong dissociator. All right, for this strong dissociator, and we see that there's a 1-to-1 ratio here, inside that solution, there's 0.0010 molar of this, and there's 0.0010 molar of this. So again, it's a situation where we have a ton of ion floating in there relative to something like neutral water. Okay? So what would we do to actually approach this problem from a Gen Chem perspective? We would say the pH is equal to the negative log of our H plus concentration, which is again our H3O plus concentration. Just going to keep reminding you of little details from general chemistry. Okay. If I put this concentration in here, what I get for the pH is I get 3.00. And that's a pretty good approximation for the pH. Now, why did I just say that was an approximation? Because what do we know now? All right. We know that in actuality, the pH is the negative log of the activity of your H3O plus. Okay. So what do we need in this instance? All right. Slightly easier problem because it's a full dissociator. We need to know, right, the concentration of H plus and the gamma of H plus. Now, why I said it's slightly easier than like the water example, that's what I was referring to, is that if you look at this, we kind of know what IC is again already. Now, this is another simple IC. ICs aren't always that easy to calculate. It's going to be 1/2, all right, the charge of H, which is 1, and we square it, times the concentration of H, which we already know is 0.0010 molar, all right, plus the charge of Cl, which is -1, and we square it, so it's 1, times the concentration of Cl minus. There's technically H3O plus from water in there. There's technically OH minus from water in there, but they're so small that this is going to give us our correct IC. So again, it's a nice simple situation where our initial concentration is our IC. This isn't always the case, and I'll eventually do an example to show that. But for situations where we have a 1-to-1 relationship in terms of the stoichiometry, the molarity being the IC is just something that occurs. So now what I can do is I can go on our table again, and I can look at for H plus, H3O plus, when the ionic strength is 0.0010, what's that gamma? And again, just kind of double check my work, as always. What I get when I look up this gamma is this gamma for H plus for this ionic strength. For me, it looks like it's 0.967. Pretty close to 1, but not exactly 1. So again, if we were doing some trace analysis, or if, you know, these decimal places in pH really matter to us, knowing that it's not 1 is important. And we're able to actually calculate the pH now in a much more accurate way. So to continue with our problem, our pH now is going to be the negative log of 0.0010, right, times our gamma, times our 0.967. Remember, you drop units whenever you're doing these logs, okay? You know that the pH is going to come out as something that's unitless for us in terms of how we look at it. And what I get for this pH is 3.014573, which is based off the activity. Now let's make sense of it. What's happened to the pH? It looks like it's slightly more basic. pH has actually gone up. It's the opposite result that we got from our last example with water. But again, you have to think about the chemistry. What's this activity actually measuring? How much free-floating H plus there is. And in a situation where the H plus is just completely ejected into the solution by the strong species, then really what this is measuring is how often will the H plus and the Cl minus interact with each other so that this doesn't look like a free-floating ion anymore. So actually get something that's a little bit more basic, right, than you would expect. So the answer here is 3.01, where before it was 3.00. All right. So you have to consider the chemistry. You have to have that in your mind. And for these strong species, knowing that they're slightly more basic when this is in that middle range of not being dilute enough to just call this concentration, but also not being concentrated enough that some goofy things start happening, knowing that you'll kind of have this slightly basic uptick is important, right? And I just mentioned some goofy stuff that happens. All right. Let's look at a very famous plot. And let's monitor gamma for H plus as ionic strength increases. So one way that you can view this plot is what happens if we keep going higher and higher molarity of HCl? What do we expect to happen? It's not a continuous thing, right? So what we're going to put on this axis, right, is we're going to put gamma for H plus. On this axis, we're going to put ionic strength. On this axis, right, I'm going to note down where 1 is, right? Because remember, that refers to like an ideal situation, all right? When our ionic strength is really low, right, our gamma for anything is 1, because remember, for these solute particles, right, these things that are in water, when there's a low amount of them, it's dilute, it's ideal, all right? Gamma is 1, and the concentration is all you need, right? I'm going to emphasize this by just kind of drawing this line here like that, okay? That's exaggerating it, but it's okay. Just want to really hit that home. For dilute situations where you don't have a lot of ions, all right, you do get a gamma 1, and a concentration is what matters. What we see here, though, is that as the ionic strength increases, for something like a strong species, remember, we're kind of considering HCl here. As we increase the molarity of HCl, the ionic strength goes up. So as we're increasing the ionic strength of HCl, you're going to get more H pluses and Cl minuses pairing in solution, finding each other, right? And what you'll see is it looks like there's less free-floating H plus and Cl minus, so gamma for H plus goes down. And it kind of forms a trough. And the way that we view this trough here is essentially there's not enough water to keep the H plus and Cl minus apart. So when we think about the activity, right, of H plus, when we think about its chemical behavior in the context of free-flowing H plus, there's simply not enough water. It's too concentrated in terms of H plus and Cl minus. The H pluses and Cl minuses are feeling each other too much. And then so what we're ending up with is a situation where the activity of free-floating H plus is going down. Eventually, though, there's this turnover. And eventually, as you get to extreme molarities, which would be extreme ionic strengths, you end up with this gamma going way above 1. Now, what's happening here is, essentially, H plus is no longer a solute, right? In this region right here, where we have such an extreme molarity that the ionic strength is really, really big, there's not enough H2O to hold the H plus at all. There's almost not enough H2O to dissolve it. It's hard to dissolve it. And I don't know if you've ever seen like HCl in its concentrated form where you've kind of noticed that it has a vapor pressure that's pretty high. Vapors come off of it. It's almost like your gamma's above 1 now. It's almost like there's repulsions. But like I said, it's not that there's molecular repulsions like when we made those arguments with Raoult's law. It's almost like there's just, what's really happening is there's just not enough H2O to keep those molecules in solution. To actually eject more H plus, right, HCl, it actually just kind of looks like your entire standard is breaking down. And why is your standard breaking down? Because it's no longer a solute. Okay. So for example, and knowing that there are some physical, again, arguments we can make for what we see in terms of activity is really important, right? So as an example, gamma for H plus, right, at an IC that's 10.00 molar is 10.44. Okay. So it's just a really strange situation. If I want to take the pH of 10.00 molar HCl, that's the negative log of gamma for H plus times the concentration of H plus. Well, I know this is a 1-to-1 ratio here, so this is equal to the negative log of 10.44 times 10.00. Concentration of HCl is the concentration of H plus. I get this as a negative 2.0187 pH, something that's saying, hey, there's a ton of acid there, all right? There's just a ton of acidic behavior. The activity of that ion is ramped up because essentially there's no water there to keep it at bay. So again, it's kind of like you have to change your thought about how the solution is being analyzed, because H plus in this instance is no longer a solute. It's not the easiest thing to grasp, but just kind of realize from a practical standpoint, what are we doing again? We're finding a gamma based off of the physical process that's being enacted. This gamma came from an experiment in this case, right? We include that gamma as getting an activity instead of just a concentration, and what we see is an actual pH that we will be able to record for that situation instead of an approximate pH just based off of concentration. So, a couple other details for this video I want to go over. I keep mentioning these gammas are coming from our tables, or they're things that we can measure. We can do some theoretical work to determine what gamma is equal to. All right. And so we're going to briefly mention, and then we'll talk about how to use it, Debye-Huckel theory. So what happens when we don't have an experiment that we can do for gamma, all right? There's no experiment we can do, like even a pH. A pH we can use to get gamma, right? Because we know what the concentration is. We can go ahead and infer gamma by seeing what the measurement of pH is, because we know pH is based off activity, okay? But what happens if we can't do that? Debye-Huckel theory says, and there's a lot of theories that predict what gamma is, and this is just one of them. It's the one your book uses, so it's the one I'm going to go over. The natural log of gamma plus minus, and I'll talk about what that means in a second, looks like this number, which is negative 1.173, times the charge of your first ion, charge of your second ion, multiplying each other, but then you take the absolute value. IC to the 1/2 over 1 plus IC to the 1/2. And we don't really need to know where this is coming from. We just need to know that it's a theoretical method that we could use. If we couldn't do an experiment for gamma, it's going to give us an approximate form of gamma. What do we need for Debye-Huckel theory? We need the ionic strength of the solution. If we know the ionic strength of the solution, we can go in here and we can infer what gamma plus minus is. Now, what gamma plus minus is, all this is saying is that for your cation and for your anion, gamma is equal. So really it's saying gamma plus and gamma minus are going to have this same value. Now that's a major drawback, all right, for Debye-Huckel theory. It's a major issue that we have with Debye-Huckel theory. Again, in the absence of experiment, we'll use it, sure. But gamma plus being equal to gamma minus, right, that infers that the ions have the same ionic atmosphere. That infers that the ions are going to be behaving the same in solution. It assumes that they have the same size. And we see from our table that that's not always the case, right? So you use this guy in a reaction last semester when you did the iodine clock. Now you don't remember that you used it, but you did. And what you found was you got a gamma that was like 0.7. Now the gamma didn't really affect your calculations that much, okay? But getting a gamma that's 0.7 means that gamma is not 1. And so that means that you should be considering activities instead of concentrations for those sorts of situations, okay? So this is the main issue that we'll have with it. We'll remember that this is an issue when we do analyze the use of this. We see that when we do use Debye-Huckel theory, all right, we do it in an iterative fashion, okay? So we do it for a setting with an assumed IC, and then we calculate our answer. We get a new set of concentrations, calculate a new IC, and you start over and over again. That's just a little bit of preview. I promise I'll walk you through that in an example problem later on, right? I mentioned this before, I might as well just write it down too. So what sort of experiments can we do? A lot of the experiments, because I'm talking about ions, are electrochemical experiments, and I think Dr. Richardson talks about a bunch. I know I just said this in words, but let's say that we're doing an experiment and we can do something like for H+. That's the easiest way to kind of think about it. And then you can design electrochemical experiments that do something similar. So you put your pH probe in there and you get a pH, right? You know that that pH is the negative log of activity of that H+. You know that activity can be written as gamma H+ concentration H+, right? So what if you know this, or you have a way of determining that for sure? If you can measure pH, that's a number you can put there. If you know for sure what that concentration is, not the activity, right? But what that concentration is, right? That's a number that can go there. And then so what you can do in those situations is you can solve for gamma H+, okay? Now, like I said, from an electrochemical standpoint, you can do this with other techniques. I honestly don't know a ton about it, all right? But theoretically, it kind of makes sense. If you can find a way to infer activity and you know concentration, so you do some experiment where you can get the activity and you know the concentration, then automatically you know gamma. And that's what we're showing here. So we could do a theoretical calculation of gamma, like we just showed with Debye-Huckel theory, or there's going to be some experimental techniques where we're able to get an experimental gamma and then we throw them in a table like the one I sent you, okay? Now, why is this incredibly important to keep in mind? I've been justifying it along the way. I'm going to justify it one more time in another context, all right? To really compare reactions, all right? Ionic strength should be consistent. So what you'll see in the organic literature, for instance, or other literatures where you're looking at these systems where you're looking at chemical behavior under different conditions. So for example, rates of reaction at different pHs. One thing that you'll have to assure when you're doing these sorts of experimental analyses, and now that we understand activity exists, all right, you have to keep IC the same. So think about that. We know that IC affects gamma, so it's going to affect pH. But I want to run a reaction at pH of 1, and I want to see what the rate is. And then I want to run the same reaction at pH of 2 and see what the rate is. If you're just going to isolate the effect of pH on that situation, you have to make sure that you keep IC the same. Because if I just change the pH without keeping IC the same, all right, then there could be other effects that are affecting the rate, not just pH. There could be ion pairing, there could be ionic atmosphere interactions that are going on that change because there's different amounts of ions in solution. Changing the pH changes the different amount of ions in solution, so the chemical behavior might change just because of that. So then I can't really compare those reactions that I'm running at different pHs. Even though it's the same reaction with just a minor change, I really can't compare them because the ionic strength isn't the same. So what do you do in these situations? You throw in salt. You throw in something like KCl, all right? So that the ion strength in each solution is the same. So then you're really looking at just the differences in concentration instead of the differences in chemical behavior as you modify pH. This is just one instance where it comes into play, and Dr. Dan, can tell you more about this because he did a lot of rate work with his research. And whenever they set up a reaction solution to monitor the chemical rate, the kinetics of that experiment, they make sure that IC is consistent. Something like KCl is not going to be involved in a reaction, but what does it do? It gives us pluses and minuses that keep the concentration of pluses and minuses the same. So it's something that definitely needs to be considered when you look at reactions. So what we'll do from here on in is we'll look at actually doing more problems, like full ice table part analyses with activities in mind. I think we've justified it enough physically. Hopefully you kind of get what's going on from a physical perspective and why we really need to consider activities and not concentrations. But again, one of the main points from this video is that you definitely have to consider the chemistry involved. You consider how you analyze the result, all right? It always goes back to that main equation that you're looking at and what activity is doing to that equation to actually modify the behavior of the species in that reaction.